Hi all, welcome to another video of compressible fluid flow video lecture series. So in the last class we have discussed about momentum equation, which is otherwise known as conservation of momentum, and we have tried to derive an equation for this momentum equation. For that purpose we have considered the system and control volume approach. So basically what we have done is to find the momentum flux through the control volume that was considered, and using the Newton's second law of motion we have started with an expression like this: sigma fx is equal to d by dt mcx, which is actually, as per the Newton's second law of motion statement, total force in x direction will be equal to rate of change of momentum in that particular direction. So we have taken the direction as x direction. Now after that, the momentum in final state and initial states were found, and we have also found the rate of change of momentum in the control volume also, and we have substituted in the initial expression of the total force, and we have also found the outflow of the momentum flux and inflow of the momentum flux. And after substituting the values of the momentum in control volume and momentum in outflow and inflow, we have finally reached an expression like this: delta fx is equal to the sum of rate of change of momentum in control volume plus momentum in outward flow minus momentum in rate of change of momentum in outward flow minus rate of change of momentum in inward flow. And this was explained as a statement. Now after that we have considered the mass in the control volume, elemental mass in the control volume, as rho dV, and the elemental entry and exit areas of the control surfaces as dA inward and dA outward respectively. Okay, now we are changing the rate of change of momentum in the control volume in terms of density, like we have done in the continuity theorem. So dou by dou t integral CV is integral for control volume. This mass m term is converted to integral rho dV, like we have done in the earlier case, and a Cx also will be there. So rho Cx dV will be the final form. We can also take the partial derivative with respect to t inside the integral CV. Now integral outward flow, for the outward flow we will also change the expression in terms of density. So integral outward Cx dm dot is changed to this dm dot is changed like this. This is mass flow rate, change in mass flow rate. So mass flow rate, like in the previous derivation, we know that it is actually density into velocity into area. So dm dot will be converted to rho into Cn into dA out. Since we are taking the outward flow, we need to take the surface area, control surface area, dA out. Okay, and an extra Cx will be there, since it is since we are dealing with momentum rate. Okay, and this Cn represents the normal velocity from the area dA out, and this is simplified like this: integral outward rho Cx Cn dA. Now in the similar fashion we can find integral inward also, integral for the inward flow also, that is integral Cx dm dot, that will be changed to integral Cx rho Cn dA in for inward area on the control surface. This is also changed in terms of, this is also rearranged: integral inward flow rho Cx Cn dA, just like the before step. Now substituting these equations, substituting these final forms in our earlier expression, that is sigma fx. So all the terms are converted to integral forms, and all the terms consists of the density term also. Now this can be considered as the integral form of the momentum equation. Now similar expressions for y and z directions can also be shown like this. For y direction we will change the suffix x in the previous expression by y, in the case of force also, in the case of velocity, also. Okay, we can change the direction. For z direction also we can show the expression like this. Now here also we will take the vector notation of the equation. So before stating the vector notation, let us see with respect to the diagram. In the previous derivation we have seen that in vector notation we will take the final state minus initial state. We will take the value of the final state minus initial state. That will be considered as a positive value if we are taking the vector notation. So in the previous case for continuity equation, it was given in the equation, in the expression, while the derivation we have seen that in the equation itself it was inward flow minus outward flow. That's why a negative symbol came. Okay, that was explained in the previous video. But in this case, in this momentum, rate of change of momentum equation, we can see that our equation consists of outward flow minus inward flow. Okay, it is outward flow minus inward flow. Therefore, in our vector notation, this whole term will be positive. Okay, instead of inward flow minus outward flow in the case of continuity equation, here in the momentum equation we have outward flow minus inward flow. So we can take this in the vector form as a positive value. Okay, therefore in vector notation equations can be expressed by a single general expression like this. Delta f, we have taken the x notation because this is vector notation. So dou by dou t is taken outside. Dou by dou t of integral cv rho c, we do not need to show the direction for velocity also, rho c dv plus, for vector notation, this whole outward minus inflow outward minus inward can be shown as a surface integral of controlled surface. Okay, rho into c into dA into c, all the direction notations are taken away. Okay, so z and n, all those things are taken, and also this will be a positive value since we have outward flow minus inward flow, so this is taken as a positive value. Now this is considered to be a final form of vector notation. We can also change this equation for it's a simplified form which can be used for problem solving and analysis. For that purpose, we need to consider what all forces this F comprises of, this delta F comprises of. Here, total force includes body forces, like body forces consists of inertia, gravitational force, electromagnetic force. All these forces will be body forces. And also surface forces also will be the surface forces will be friction, pressure, and surface tension forces. These forces will be coming under surface forces. Now we will consider a steady flow. In the case of steady flow, we can take this term equal to 0 because dou rho by dou t will be equal to 0. So this entire control volume term will be equal to 0 in the case of a steady flow. Therefore, the other term in the equation, that is integral rho c dA into c, will be equal to our total force. This will be the change for steady flow. Since this term will be equal to 0, delta F, that is total force, will be equal to surface integral rho c dA c. So if we are taking steady one-dimensional flow, we can give notations for initial state and final state. For initial state, we will give the notation 1, and for the final state, we will give the notation 2. Since this is positive value for surface integral, we can take from the vector notation like this, final value minus initial value. Therefore, final value will come first. So rho 2, A2, this dA is integrated, then it will become A2 into, there are two fluid velocity terms here, therefore C into C will be C square. So giving the suffix 2, it will be C2 square. Therefore rho 2 A2 C2 square minus the initial values rho 1 A1 C1 square. This is our final momentum equation. We can find the total force from the momentum equation. This is also considered to be a part of a derivative of our momentum equation. Okay, so this is the end of momentum equation. Next, we have to discuss about energy equation that we will be discussing in the next video. Thank you.